Hello, everyone, and welcome to part 7 of our series of seminars on SolidCAM's 5-axis simultaneous simultaneous machining, given by Ahmad Onkar. Again, this is being recorded as always, and will be available on our website later on. Before we start, again, I'd like to remind everyone to sign up for the SolidCAM World 2018 in Tübingen, Germany. We're getting close to the date already. It's less than 2 months away. So please sign up as soon as you can. This way you are guaranteed also a room as close as possible to the actual SolidCAM World, to the SolidCAM World itself. Okay, Ahmad, I will make you presenter, and you can go ahead. Just a moment. Okay, you can go ahead and show your screen.
Thank you very much, Sydney. Hi, everyone, and welcome to the webinar. I was asked by some people in SolidCAM and also some resellers to refocus on the multi-axis roughing, on how it is done and how it works. And we're going to see another aspect of 5-axis today, the application-based 5-axis, which is the screw machining. So these are the two subjects we are going to see today. Today's webinar will be the second last webinar. We're going to have one more next week of 5-axis, where I will touch upon the port machining and contour 5-axis and multi-axis drilling. So these are some of the aspects that we are going to look at. So I'll start off with our multi-axis roughing. So multi-axis roughing basically works in a very simple mode. What it basically does is it will look normal to the floor surfaces, and the tool axis will always be normal to the floor surfaces and machine the walls that are adjoining or that are connected to the floor surfaces. Now, for some reason, if your walls are having drafts or if they are not normal to the floor surfaces, the resultant wall surface will always be normal. So it might either leave material at the bottom or it might leave material at the top. But it will not eat away material from your part, but it will leave material if the walls are not normal to the floor. So the philosophy is that the tool axis is always normal to the floor surface, irrespective of how your wall surface is. It will always create the wall which is normal to the floor surface. So in this part, what I've done basically is I've done the eye machining 3D to remove the material. And then I've closed the top to generate an HSM linear machining to just make it ready for multi-axis roughing. And then I've generated the swarf surface on the side, where the side areas are completed. So I have got a block that looks almost like what is seen on our screen, except that there are no pockets generated. And these pockets, along with this cutout, will be done in multi-axis roughing. All right. So what I've done is I've saved a template for this particular part for multi-axis roughing. So I'm going to add an operation from the template, and I'll use the same name, 5-axis roughing. Okay. So I've now generated the operation, and now I need to select the geometry for my calculation. So in our geometry, we have got a couple of things. First is the strategy. We are going to see both of them. We'll see the offset strategy, which is very similar to our contour roughing in HSM. And then we have the adaptive strategy, which is very similar to eye machining. Eye machining works in 2.5 axis. Eye machining works in 3D. Also, eye machining works in a wrap mode in 4 axis. This, you could say, looks or you could give a name to it, saying that this is iMachining in 5-axis. Apart from the strategy, we have got the way the strategy works. We can have offset from floor, that is offset from the floor surface, which are basically these surfaces, and there is offset from ceiling. Basically, ceiling is the topmost surface out here. So it either will go offset from bottom or offset from top, which is the ceiling, or it could morph between the ceiling and the floor. Okay, if your ceiling surface is not exactly parallel to your floor, then you can probably use this particular strategy. Okay, so the floor surfaces that we are going to see today are these surfaces. So I've picked up the 4 floor surfaces, and on the wall surface, it's basically these surfaces. So I have pre-selected already the wall surfaces for my operation. I'll be keeping about 0.5 millimeter stock on either of these surfaces. And in the tool today, we are using a 20 bull nose, corner radius of 2 millimeter. You can use any tools in this. You can use a flattened mill. You can use a bull nose tool. You can use a ball nose tool. You could use any of these standard tools to machine it, which is itself is a big advantage for 5-axis, which otherwise people generally would use always a ball nose tool. This allows you to use standard bull nose, standard ball nose, and standard flattened mill. In the levels, there's not much to choose from except that we are going to have some safety distance, entry and exit safety distance. You can see that most of the areas are grayed out. That means these are taken care by the system automatically. In the constraint boundaries, unless and until you want to specifically machine a certain area, you could leave the boundary type to automatic, because it's anyway not going to machine anything out of the surfaces that you have just selected. Let's come back to our toolpath parameters. The biggest mistake that I've seen people working with when they do with multi-axis roughing is the tolerance. Remember that this is a roughing operation, and there's no point in keeping a tolerance of 10 microns. You're only going to increase the calculation time. So we'll need to open up the tolerance. So we are going to make it 0.1. Step down. That means either we can define depth of cut, or we could define the number of slices, how many slices we want in this. You can also define your first step down and your final step down. In event that you don't want your first step down to be exactly at 0, you would like to go slightly below, then you can put the first step down as a value and the last step down also as a value. In this case, we're going to use a step down of 2 millimeters, and our maximum step over is going to be 8 millimeters. Okay, we are using a 20 dia, so I'm going to go slightly below the 10 millimeter. That's half of the corner or half of the radius of the tool minus the radius, the corner radius. In the sorting, we will have one-way machining, and it's going to be a pure climb milling, and we're going to machine by regions. That means it's going to finish one region first, then jump to the other region, then finish the next, and then the last. Smoothing, we will use the corner smoothing, okay, and also the links smoothing. And since I have defined exactly my surfaces that need to be cut, I don't need to define the stock model, or I don't need to define the rest rough. For rest rough, we will see another operation after this. Okay, in the link, I'm going to define my ramp angle as 5. Ramp type is auto. That means it could either ramp using a helical, or it could ramp, depending if it doesn't have place for doing helical, then it could do a linear ramping, or it could do profile ramping. So you have got several options here, and auto will choose the best possible method of ramping for that particular geometry. In the approach and retract, my first retract from the first entry into the job, it's going to use the ramp. Okay. In the links within the group, it's direct. We are not going to use any ramping. Between the groups, we are retracting to the rapid distance, and we will use ramp. Between the slice, it will retract again to the rapid, and we will use ramp. And between the regions, it will again retract to the rapid distance, and we will use the ramping. All right. There's nothing more to work with, so I'm going to save the operation, and we'll hit the calculate button. The calculation would take anywhere between 30 seconds roughly. Anyway, it's already done. That's pretty quick, and this is one of the reasons why you need to have a tolerance which is pretty open, okay, not something that's pretty closed. So I have a nice toolpath, and now we can run the simulation. Solid verify. Okay, it's calculating the previous stock. Okay, the stock has been saved and it's visualized, and I have some extra stock that is remaining because I've already done the outside swarfing, and I don't want to see this extra stock dangling out, which doesn't seem to be connected to the main stock at all. So we will use the stock show and hide, and I will select from solid 2, solid 3, solid 4, solid 5. So I will select all of them, right click, and I'll delete them, and I'll just show this one. So I've removed the unwanted stocks from my, because anyway these stocks are going to fall down once it actually goes into the machining, so there's no point in keeping it. Let's do the simulation. You can see that it's doing a pretty neat ramp, and then it goes in. You would have wondered what has it done here. That's because there is a small step out there. It's trying to machine, it could not, because the step over is too large. So it's left that area unmachined. Okay, it's done this pocket, and now it'll go to the next pocket in this. There it is. You can see that it's already done that step, but it is still left out some material that could be removed out in finishing. We know that the corner here is about 8R, except one corner out here on this side, which is slightly bigger, where all other corners are R8. So we know that we are going to have material left out in the corners. So we will need now to have a toolpath for doing rest roughing. Okay, let's increase the speed. Okay, that's done. So it's nicely done, a 5-axis kind of a roughing. And if you run the machine simulation in this case, okay, it's not found the machine, so we can go into a different machine. Oh, we have it. Let's take this one. Might have to run the calculation again. Yep, let's calculate this. Okay, let's run the second calculation again. This is pretty quick. Let's check. We already have the setup ready. So let's run the simulation. Oh, sorry. Okay. Let's exit and run the machine simulation again. Yes. Okay. So we have that over here. Going to switch off the toolpath and run it. You see that it's pretty much doing a nice 5-axis kind of a cutting. And if you want, actually, this is a very nice part to show during any exhibitions or demos on the capabilities of SolidCAM 5-axis. So it's a pretty nice part. You can show multi-axis roughing, you can show swarfing, and you could also show our generic 5-axis machining by using morph between two curves or parallel to the curve and show the wall finishing using our generic 5-axis. Okay, so let me come back here and I'm going to copy this operation and paste it. So what I will do is first of all rename this one, and here I'm going to use 10R1. Okay, and let me edit this toolpath, and everything remains the same except that I'm going to change my tool to, sorry, it's 10R2. So I'll change the name here to 10R2, and I'll go to the toolpath parameters and I'll switch on my rest rough, where it asks me what is the previous diameter. If your geometry selection is right, and if the first operation calculates very quickly, so that's the first thing to notice out, that your calculation is pretty quick when your geometry selection is right. If you select a lot of unnecessary geometries, then it loses a lot of time in sorting out geometries which are not needed. So if your geometry selection is right, I would suggest you to directly jump into rest rough. But if your geometry selection is not right, then you need to go back to the stock-based rest roughing, which is a pretty long procedure. So in our case, we know that the geometry selection is right. So I'm going to pick the tool that was there used previously. So it's a 20R2 bullnose, and the previous roughing offset was 0.5. So that's my basic thing. And in my link, I'm going to switch off. I don't need ramping now. So I'm going to switch off ramps. No need to use any ramp here because it's anyway rest roughing. Okay, so just save this operation and let's calculate this. Like I said, except one of the fillets, every other fillet is R8, so we should see toolpath in every other regions except one of them. It's generated the toolpath everywhere, and that's one of the reason being our previous roughing offset. If I give it as 0.6, then I think we should not have any issues here. It's 4. Let's save it and let's run the calculation again. Hopefully we should get a better toolpath now. calculation is thinking that it still has material on the walls, but trust me, in most of the cases, you'll only get the toolpath on the corners. So I'll have to figure out why this thing did not work. But anyway, this also looks to be a pretty good toolpath at the moment. So let's run the simulation. The thing to remember in multi-axis roughing is that if your floor and wall surface are not normal to each other, then you could end up getting a toolpath that's unexpected in some cases. So you need to choose your parts pretty wisely when you're doing multi-axis roughing. The term multi-axis roughing sometimes it's basically deceiving, because in most of the cases, multi-axis roughing, the user thinks that no matter what is going to be my wall, it's always going to be parallel to my wall. The tool axis is going to be parallel to my wall, but that's not the case. The tool axis will only be normal to your floor surface. So whatever is the end result is going to be the wall. So what the surface that is going to be generated at the end, the wall surface, will always be normal to your floor surfaces. So that's one key thing that you need to understand in multi-axis roughing. Okay, so that's what we have here. And let's run it pretty slowly. Right. There is some air passes. That's because it's unnecessarily running in some areas. But otherwise, it's almost doing a semi-finishing kind of an operation. Makes it ready for my next finishing operation, which could be any generic operation in this case, or it could be even a swarf kind of an operation to finish the walls. All right. So, like I said, SolidCAM's multi-axis roughing can be used to rough out parts you're seeing on the screen out here, where you have the tool axis will be normal always to the floor surface, and it will cut the adjacent walls in that particular tool axis only. So you could have a situation where if your wall is not normal to your floor, it could either leave material at the bottom or the top, depending on how the wall surfaces are. Right, we'll move on to our next part, where we are going to do a completely different kind of operation, and that's going to be our screw machining. Now, because screw machining takes some time to calculate, I'll not be doing the calculation in front of you, but I'm going to explain to you the fundamentals and how it works in our case. Screw machining basically is it's basically a rotary machining, which means you can machine almost any part in which the tool axis is around or rotated around a certain axis. In our case, you can see that the tool axis or the part is being rotated around X. And the tool is always going to be normal to the rotating axis. So it need not be just a screw. For example, in about a week back, we had a part which was, if I show you, I can't show you the part because of some confidentiality issues. There was a part that was like this, and then like this, almost like a cam. And it was rotated from the center of this hole. So our rotation axis was here, and the entire part was being cut out from a square stock. So you could use screw machining also to do roughing of these parts, where you need to remove material where the axis is rotated around a particular, or the tool part is rotated around a particular axis. In our case, it was rotated around X. So you could use screw machining to scoop out material from this part. But classically, screw machining is used for machining such parts like an extruder screw. Now, it's pretty simple because screw machining works on what we call as an application-based strategy. So the inputs are very, very little. What you need to do in screw machining? In screw machining, you need to define what you're going to do, whether you're going to do roughing or whether you want to do finishing. And what is the offset in this case? What is the pattern? In this case, we have used an offset. You could also have a pattern called as an offset of spiral, where open portions will be done in spiral kind of a machining, whereas the profile areas will be done using the offset method. As far as machining surface goes, there is no need to select individual faces. You could just select the part model, which is basically defined as STL geometry inside the software. And what is the offset that you need after roughing? What is the material that it needs to leave for finishing? So it's basically simple 3-axis kind of a roughing, except that the tool axis is now rotated or wrapped around a particular axis. The other thing that you need to define is machining axis, or what is your limits of machining. Now, the limits can be defined in two ways. It could be axial, which means I can define, in this case, that the software should machine from this point onwards to this point. So this is my axial limit. Or I could specify that you machine between this and this point, 2 points. So that becomes my axial limit. Whereas you have another option called as an angular limit, wherein I can go to the side view, okay, in this case, this side, and I can say machine from 0 to 90. So it will only machine between those two angles. So if I go back to my part here, I can specify that you please machine between only these two angles, because I know that this side there is not much of a material and that could be removed with some other method. So I can ask the machining to happen only between these two angles. So it could be 0 and 200. Okay, so it will machine only between these two angles. So, and the limits can be defined either using the axis values or by angular values. The tool, we support basically the standard tools, end mill, bull nose, and ball nose. Okay, we don't support any special taper mill in this case, but here we have used a 20 corner radius 3 bull nose tool. Levels, you can see most of the things are grayed out and they are selected automatically. The only thing that you are allowed to change is the retract distance and the safety distance for entry and exit. Toolpath parameters, like I told you again for multi-axis roughing, the tolerance plays a critical role here in terms of the calculation speed. So you can have an open tolerance for roughing, let's say 0.1, the depth of cut, and side step. As simple as that. There's nothing else here. Sorting, we can have zigzag, and in the stock, I'm going to use I've used the auto updated stock. You have auto updated, you have surfaces, or you have bounding cylinder, because in this case we can use the surface mechanisms and select the cube here as a surface, stock surface, and run the roughing. Tool axis control, I can define what is the output format. Screw machining only supports 4-axis machining, so there's no other possibility of doing 3 or 5 axis. The only thing that you could change here is the rotary axis. In our case, we need the machining to happen around x-axis. Okay, once you have defined your links and other things, it's very similar to multi-axis roughing and the tool axis. You can hit the save and calculate button. There have been some reports that people feel that it's pretty slow in calculation, but unfortunately, or fortunately for us, there is no other product that you can actually run a comparison against, because when you say slow, slow is a quantitative statement. That means slow against what? If I take 20 minutes to calculate, I need to have another system which probably take 10 minutes to calculate, and then you can say, look, we are slower than system A. But unfortunately or fortunately for us, there is no system to compare it against with, okay? Because this is a pretty simple part that I'm showing you. So for example, this was calculated in about 3 minutes, and this was our result, okay? So we generate immediately tool paths like this. Looks simple, but if you really take a generic 5-axis kind of an operation and try to generate this tool path, it's virtually impossible to generate this tool path. Using the same method, we can, instead of roughing, I could say just generate a simple finishing operation, and this is what will be our result. We will have a finishing operation. So I'm talking about a total calculation time of 5 to 7 minutes for this part, for one roughing and one finishing operation. Trust me, 7 minutes just to do this part is nothing. If you try to use a generic option, then you could end up spending anywhere between 1 to 2 hours. So when you compare against that, we are really fast in calculation. Now, what else this can do is defined in our next one, because that was a pretty simple part. Now, what you'll see now here is a pretty complex part. Okay? Now, you can look at this part. This part is about, if I measure, sorry, let's pick this face and this face here. This is about 2 meters in length. Okay? 2 meters in length, and the diameter roughly is about 106 millimeters or 107 millimeter diameter. The depth is about 15-20 millimeters, and plus it has got this cutouts, strange cutouts on the screw. So when you have parts like this, you can really forget doing this in our generic 5-axis, and then you shouldn't be complaining that it's slow or fast. For example, this roughing on this particular part took about 12 minutes to calculate. It's very fast, to be very honest. It's very fast. 12 minutes for this part. You could be spending few hours on this part trying to figure out how the tool path would come out using a generic 5-axis. Whereas just selecting the part, selecting the axial limits, selecting the tool, selecting the depth of cut and the side step would take you not more than a minute to define and about 12 minutes to calculate. And the same thing can be done, or finishing can be done in approximately another 10 to 12 minutes, just by selecting a different tool, different down step, and a different side step. So screw machining is very powerful for machining any geometry that is running around a particular axis. Like I showed you a part using drawing, and I also showed you 2 parts where we did the roughing and finishing of a simple extruder kind of a screw and a very complex extruder screw, because this particular part that you're seeing is about 2 meters in length. So it's not a small part, and plus it has got geometries that are pretty complex. All right, today's webinar unfortunately had to be a pretty small one because I touched upon a subject that was already done and a new subject where there's not much of a calculation that I could show you because of the time limitations. If I had done the calculation of all of them, it would have taken about half an hour for me to calculate, which is to be sheer waste of time in a webinar. So today's session, we saw multi-axis roughing and screw machining. In the next session, which is going to be our last session, we'll touch upon port, we'll touch upon contour 5-axis and multi-axis drilling. So if there are questions about this particular session, I'm open to answer your questions. Sydney?
Okay, Amaz, I'm not sure if you take a look at the questions now, I'm not sure if they're related to this particular webinar.
Okay, there are some few questions here, and I would like to just answer them. About the first question, all the 3 have been asked by a friend from Russia, and I did not explain the 5-axis contour. I'm going to do that in the next webinar. And also, he says that I don't understand how to use feed rate optimization in feed control. He wants us to explain this function. I will do this, Andre, next time about feed rate optimization. Although I've already done it before, I will explain to you how it works.
Okay, excellent. Okay. All right, everyone. Thank you very much again. Amod, thank you very much for the webinar given today. And we will see you again all next week for the
Yeah.
last of this of these excuse me, of these series of webinars that will be given by Amod on the issue of 5-axis simultaneous. Everyone have a great weekend. Take care.
Thank you.